Good morning, everyone. It is my great pleasure to be here to present our recent research on dynamic binary translation. The first author, Changheng, cannot be here due to a visa issue, so I will help him to present the paper. Okay, let's start. Dynamic binary translation, or DBT for short, is a key enabling technology. In general, DBT systems translate binary code from a guessed instruction set to a host instruction set and execute the translated host binary code. Previous studies have shown that in most cases, the execution time of a DBT system is mainly consumed by executing the translated host binary code. So generating high-quality host binary code is very important to the efficiency of a DBT system. To implement DBT systems, a common way is to use intermediate representations, or IR. We can firstly translate the guessed binary code to IR and perform optimizations on IR to generate efficient host binary code. However, this approach has at least two limitations. First, the runtime optimizations can introduce very heavy translation overhead. This is undesirable for a DBT system, especially for short-running guessed applications, because the execution time of these applications is mainly consumed by the translation process. Another limitation of this approach is that it requires a significant engineering effort to support different host architectures, because the host-specific optimizations need to be redeveloped to support different hosts. To address these limitations, our previous research work proposed a new approach to automatically learn binary translation rules. This is inspired by the observation that the binary code compiled from the same source code using the same compiler for different architectures are semantically equivalent. From this observation, we can directly extract the translation rules from the compiled binaries. These translation rules can map guessed instructions directly to host instructions. Better yet, if the original compilation process incorporates optimizations, the extracted translation rules will also embody these optimizations. Now let's see how this approach works. First, during the compilation process, the guessed instructions and the host instructions that correspond to the same learning scope are extracted. Here, the learning scope is one line of source code. Each pair of the extracted guessed and host instructions form a translation rule. Next, to guarantee the correctness of the learner translation rule, we need to verify them. To achieve this, we verify the semantic equivalence between the guessed instructions and the host instructions in the learner translation rules. Non-equivalent translation rules are simply discarded. Finally, during the translation process, the learner translation rules can be applied to translate guessed instructions into host instructions directly. With this learning-based approach, we already achieved 25 performance improvement compared to existing IR-based translation approach. The question here is, can we further improve the performance using this approach? This figure shows the translation coverage achieved by using the translation rules learned using this approach. Here, the coverage means the percentage of the guessed instructions that can be translated using the learner translation rules. For those guessed instructions that cannot be covered by the learner translation rules, we still need to go through the original IR-based approach to translate them. As shown in this figure, we can only achieve 55% coverage. That means almost half of the guessed instructions, we cannot use the learner translation rule to translate them. So if we can harvest more translation rules during the learning process, we can potentially improve the translation coverage and generate more optimized binary code. This is the motivation of this work. To achieve this, we must address some limitations in the original learning-based approach. The first limitation is about the limited learning scope. In the original learning approach, the learning scope is limited to one line of source code. Although this can simplify the design of the learning approach, it may also miss many potential translation rules. Let's see this example. In this example, we have 2 lines of source code. We can use a compiler targeting for ARM, for example, LLVM ARM, to compare them to ARM instructions. Here we use the same color to indicate the source statement and the corresponding instructions generated from this source statement. Also in this figure, we have 2 ARM instructions. Similarly, we can use the compiler LLVM x86 to compile these source statements into x86 instructions. Due to the optimization across the source lines, only one x86 instruction is generated. So obviously, in this example, if we use a single line as the learning scope, we cannot learn any translation rule. For the first source line, there is no x86 instruction. For the second source line, the ARM sub-instruction and the x86 LEA instruction are not semantically equivalent. But this provides us an opportunity to exploit a translation rule that span multiple lines of source code. Another limitation is caused by the strict equivalence verification. The purpose of the verification is to verify the register and memory equivalence between the guest and host instructions in the learned translation rules. However, this equivalence verification may also discard many potential translation rules. Let's see this example. In this example, the source line x++ is compiled to 3 ARM instructions and 1 x86 instruction, respectively. To verify the semantic equivalence between the ARM instruction and the x86 instruction, the original learning approach tried to establish mappings between the ARM operands and the x86 operand. For example, the ARM register R1 can be mapped to x86 register EX. However, we cannot find an x86 register that can be used to map the ARM register R0. So this translation rule will be considered as inequivalent and will have to be discarded. But this provides us an opportunity to harvest more translation rules by relaxing the strict semantic equivalence verification. To take advantage of these opportunities, we propose the following solutions in this work. First, during the learning process, we use a sliding window to determine the learning scope. This allows us to slide through the source code and examine multiple lines of source code to identify translation rules. Second, during the equivalence verification process, we introduce the notion of constrained semantic equivalence, where a translation rule is augmented with constraining conditions. That means the translation rule are only applied when the constraining conditions are satisfied. Now, let's see more details. First, the sliding window is defined at the source code level. All source statements covered by the window are used to extract guest and host instructions for translation rule learning. Each time, the window slides forward one line of source code and slides out the last line of the source code covered by the window. By adjusting the size of the window, we can explore variable learning scopes. Let's revisit this example. In this example, if we use the window size with 2, we can learn a translation rule like this, as shown in this figure. Actually, our experimental results show that by just increasing the sliding window size to 2, we can harvest 13% more translation rules. Next, to relax the strict equivalence verification, we introduce constrained semantic equivalence. More specifically, the guest instructions and the host instructions in each learner translation rule are considered as semantic equivalent only if the specified training conditions are satisfied. For each learner translation rule, we record all unmapped guest and host registers as training conditions. At the translation stage, the training conditions are checked to ensure they are satisfied before the translation rule can be applied. Now let's see the previous example. In this example, as I mentioned before, in this example, the ARM register R0 is unmapped. So it is included into the training condition of this translation rule. That means this translation rule can be applied if the ARM register R0 is not used in the following ARM binary code. In this way, we can harvest 23% more translation rules. We have implemented these enhancements in the original learning framework based on LLVM. We also extend QEMU, which is an IR-based translation system, to accept the learner translation rules to generate host binary code. Our evaluation covers all 12 applications from the spec seen in 2006. For each application, we only apply translation rules learned from all other 11 applications, excluding the evaluated application itself. Now, let's see some experimental results. The first question we want to answer is whether this enhanced learning-based approach can improve the translation coverage. This figure shows the translation coverage achieved by the original learning approach and the enhanced learning approach. Also in this figure, we can achieve around 30% translation coverage improvement on average. This demonstrates the effectiveness of the proposed enhancement to improve the translation coverage. Next, we want to know the performance impact of the proposed enhanced learning-based approach. This figure shows the performance speedup achieved by using the translation rules learned by the original learning approach and the enhanced learning approach. And the performance baseline is the existing IR-based translation in QEMU without using any learner translation rule. Also in this figure, we can achieve around 1.7 performance times performance speedup on average compared to QEMU. And for some applications such as GoBMK and BZIP2, the performance speedup can be as high as 2.5. Compared to the original learning-based approach, we can achieve around 1.90 times performance speedup. This demonstrates the capability of this enhanced learning-based approach to generate more optimized host binary code. To conclude, in this work, we proposed an enhanced learning-based approach for dynamic binary translation. With the proposed enhancements, 1.19 times performance speedup and 13% translation coverage improvement are observed. While more work can be done to further improve the performance of a DBT system implemented using this learning-based approach, we believe the learning-based translation provides us a viable and promising direction for implementing DBT systems. This is my talk. Thanks for your attention, and I would be more than happy to take questions.
Any questions? Please approach the mic.
Hi, I would like to know what's the difference if you change the sliding window, the size of the window? You mentioned use 2, right?
Yeah.
So if I use a larger window, does that mean I can learn faster or?
It's not about the efficiency of the learning. It's about more translation rules can be learned. Because in the original learning approach, we only use one line of source code to extract the guest and host instructions. So if we use like 2 lines of source code, we can learn more translation rules.
So does it mean
Yes.
it may take longer because there's more information in there?
What mean more information?
You have 2 lines compared to 1, right?
Yeah, we just extract like this example. Yeah, we just use the 2 lines of the source code as a learning scope. And then we extract the ARM instruction, the 2 ARM instructions, and also 1 x86 instruction corresponding to these 2 source statements. And then we can verify the semantic equivalence between the ARM instruction and the x86 instruction. This provides the flexibility of the learning scope.
So we need to move on to other questions. I'm sorry. So maybe take it offline.
Yeah, we can talk more details
Yeah.
later on.
Hi, John Crizzle, University of Rochester. Nice work. One question that I have is that it seems like the efficacy of your approach, the effectiveness, depends upon what programs are actually used to learn the rules. So have you done experiments where you've changed the programs that you use for learning the rules and determined whether there's a correlation between what you use and the results that you get?
Yeah, this is a very good question. Actually, we are trying to use more programs like the Java program or program in different domains to learn the translation. But currently, we haven't done this work in this area. But it's on our calendar. Yes.
Okay, thanks.
Yeah, thanks.
How much engineering effort is required to develop the verification equivalence checker stuff? Do you have to develop that for each pair of instruction sets you want to translate between?
Oh, you mean how did we implement the equivalence verification tool?
Yeah.
It is based on an existing symbolic execution tool. The name of the tool is Fudan. And we symbolically execute the guest and host instruction sequences. And we extract the result, execution results, and feed them to a SMT solver to verify the equivalence.
Stefan Bukur from Google, very interesting work. I wanted to ask, what is your fallback strategy in case you encounter during DBT, code that you cannot translate based on the rules that you learn? Do you use fallback on IR or something else?
You mean if we cannot cover a guest instruction, how can we translate it?
Right. Yeah, so how do
Yeah,
you...
we use the existing IR-based translation in QEMU to translate them.
Okay, so
Yeah.
and then how do I identify whether something needs to go with IR or versus with the rules that you...
If basically we firstly try to match the guest instruction with the learner translation rule. If we cannot find a matched translation rule, we just go through the IR-based translation.
Thank you.
Hi, I'm from Uber. Thanks for the talk. So my question is where the new approach makes the rule space to be larger and it takes a longer time to finish the translation, even the eventual application performance would be improved.
You mean whether this approach will increase the translation overhead?
Yeah.
No, actually the translation process using the translation rule is very fast because it just match the translation rule. In the original IR-based translation, we firstly need to translate the guest instruction into IR and perform optimization on IR and then generate a host instruction. Using this translation rule, learner translation rules, we can directly translate guest instructions into the host instruction. So we can bypass all of these steps. Okay. It's very fast.
Okay, thanks.
So just one last question for me. If you look at the rules that you couldn't generate or all those gaps that you had in coverage, what was the actual reason? Do you have any kind of clue, any intuition how to, why you couldn't match these rules? Learn these rules.
The major observation is that, as I mentioned, the binaries compiled from the same source code are semantically equivalent. That's a very intuitive observation of the compilation process. And I think that's the most important thing we rely on to develop this learning-based approach and also the learning-based translation.
Okay, thank you.
Thanks.
Let's thank the speaker one last time.